Good morning. This is Professor Gina, and I am making a short video on circles and ellipses. I've started with the equation here, the standard equation of a circle. Many of you probably already know that a circle is a set of points that are all equidistant from a single point. That single point would be the center of the circle, and then all the points that are created are the exterior or circumference of the circle. And that common distance is called the radius. This is the general format for a circle. Now, oftentimes you'll see a circle that is just listed as, let's say, x squared plus y squared equals 25. It falls into this same format. We're just not writing it like this because it's overkill. But if I rearrange it into this format, we can see that for this particular case, the center of this circle is at 0, 0, and the radius is equal to 5. So when we have just x squared, both x squared and y squared, we know that we have a circle. We'll be talking in just a little bit about ellipses, which also have both the x squared and the y squared, but there'll be a distinction that the coefficients are not the same. In this case, they both have a coefficient of 1 in front of the x squared and the y squared. Sort of along those same lines, if I had something like, let's say, 5x squared plus 5y squared equals 100, because the two coefficients are the same on the x squared and the y squared, this is also going to be a circle. If I divided everything by 5, I'd have x squared plus y squared equal to 20. In this case, the center would still be at 0, 0. And in this case, the radius would be square root of 20 or 2 square root of 5, right? Because we're taking the square root of what's on the opposite side of the equal sign. Now, the standard form that we usually find circles looks a little more complicated than that. Actually, all conic sections for that matter. So let's do this example. Let's find the center and the radius of x squared plus y squared plus 2x minus 6y is equal to negative 6. The standard form that we find conic sections in will have all of the variables on one side, any numbers on the other side of the equal sign. And then we'll rearrange it to put it into the form that we can extract the radius and the center from. So step one is to put the x terms together, and then to put the y terms together. And notice that I left some space here because I'm going to complete the square for both the x variable and also for the y variable. And I'll do this in 2 separate stages. So looking at the x variables, I look at what's called the middle term. It has x to the first power. I take half of that number, half of 2 would be 1, and then I square 1, which will give me adding 1 to this side. I have to add 1 to the other side as well to keep the equation balanced. For the y variables, I'm going to look at this middle term, which is a minus 6. Half of that is negative 3. Squaring that is adding 9, and I'll add 9 on the other side also to keep it balanced. So this part becomes x plus 1, the quantity squared. Just a little note, whatever number you got when you took half of the middle term, that's the number that ends up here in the compressed form of all the terms. And then this becomes y minus 3 squared. Again, half of negative 6 gives me that negative 3. On the right-hand side, looks like we've got 4. So I'm able to see from this case that the center of this is -1, 3. Remember that we're always subtracting variables inside the parentheses. So the x, because it's got a +1, it's actually minus a -1. And then the radius is going to be 2, taking the square root of 4. So if we wanted to, we could get just a quick graph of this. The center is at -1, 3. So the center is here. And then I'm going to go out 2 in each direction, right? So I'll go out here for the radius, up here for the radius, over here, and down here. And then bear with me, this is not going to look like a circle, but you get the idea. Just make that bigger. That's the idea. Okay. Let's do another example like that. Let's find the center and radius of y squared minus 6y minus 1 equals 8x minus x squared plus 3. Now this has got the terms sort of all over the place. So what I'll do is start by moving anything that has a variable onto the left, and then anything that has a number onto the right. So the x squared is going to come over to the left. I'll move that 8x over as well. Actually, let's rearrange these so that they're in the right location. I'll put the y squared here. This will be minus 8x, and negative 6y will stay here. And on the right hand side, I'm going to have 3 and then plus 1. Let me just double check. Okay, that looks good. And then I will complete the square on both sides. This is going to be adding 16. Half of -8 is 4. Squaring that is 16. And then for the y, I'm going to add 9 again, taking half of -6 to get 3. So I've got x minus 4, the quantity squared, and then y minus 3, the quantity squared, equals 29. Yeah. Okay. So in this case, it looks like the center is at 4, 3, and the radius is the square root of 29. Let's see what that is approximately in decimal. It's about 5.4. I'm not going to worry too much about the graphs of these right now, because you can go to Desmos and you can get a graph of these. In fact, why don't we do that now? Let's open up Desmos. Give me just a second. Bear with me. I should have had this open to begin with. I'm going to switch my share here. All right. And let me just, I'm hoping that you guys are seeing this. Yeah, I think this is good. Okay. So the equation that we had was y squared minus 6y minus 1 equals 8x minus x squared plus 3. And there we can see the center is at the point 4. I think we said it was 4, comma 3, right? I can see that the center is there. And that we've got that radius is approximately 5, a little bit more than 5. So again, don't worry too much about graphing these by hand. You'll be able to use Desmos to graph any of these and see what the pictures look like. All right, let's go back to OneNote here. So let's switch gears then and look at ellipses. An ellipse, really a circle is just a special case of an ellipse. It's where, looking at these equations here, A and B are exactly identical. So we don't have this elongated feature on the circle. We've got the direction that you're going vertically versus horizontally is identical, and so you get that circle feature. So a couple things to note is that we've got two different things. We've got what's called the major axis, which is going to be the longer direction, and then the other one is called the minor axis. And within those two, we sort of have this labeling system that we use. The major axis is going to have this length be A, and then also going this direction is the variable A. And then for the minor axis going these two directions, this will be the variable B. This is the variable B. And you can see that in these cases, we always want A to be the larger number. We've got this distinction written right there for both of those. A is always going to be the larger number. So whichever variable A is underneath, whichever the larger number is underneath, that tells you which way it's going to be elongated. So in this first example here, A is under the X, and so it's stretched out in the direction of X from left to right. In the second example, we have the larger number A under Y, and so the ellipse is stretched up and down in the direction of Y. So that's kind of a way to know which direction it's going. And then the other thing to take note of is that we have this relationship, we have this other variable that's sort of behind the scenes that relates to these 2 points that are called the foci, or the foci, 2 here, and one is here and one is here. And this distance here is C. This distance here is C. And you can see we've got this relationship that's written. It's called C squared equals A squared minus B squared. It looks similar to the Pythagorean theorem, but it's actually in a different way. It's actually that C squared plus B squared is equal to A squared. So the variables are rearranged, but it is really the same as the Pythagorean theorem. It's just that the labeling is different. So I want to spend a little moment explaining to you sort of what's happening here. So let me go to back to the internet, and let's go to this. Okay, so this is on GeoGebra. I put some links to this on Canvas, and this shows you how an ellipse is created. Imagine that this green line is the one that has 2 tick marks. Sorry for those of you that are colorblind. These colors are terrible for colorblind students. The one that has 2 tick marks is going to be one of the lengths. Imagine that that's a piece of string. And then the other one that has 3 tick marks, imagine that that's a different piece of string. As I move around the ellipse, the length of these 2 segments added together, that length is going to be the same all the time. Now, one of the things that's sort of an interesting phenomenon, and it's sort of hard to see at first, is that this distance, the green plus the red, these 2 segments is going to be a total of 2 times A, which is the major axis on this ellipse. And so I want to try to show you how I would know that. So I'm going to get really close to, I'm thinking about if I were to go right here, right, and add these two terms, but I'm gonna open it a little just to show you. The length of the longer piece here is it's 2c plus this little segment. And that little segment is showing up twice. And so what ends up happening is this is a distance of 2 times a. Let me bring up a whiteboard to show you what I mean. If the origin is here, and we have one, here's C, right? This is the foci. We have one of those lengths going all the way across. The other foci is here, and this length is going from here to here. These two are on top of one another when I'm at that particular location. If I take this little piece right here and I move it, it is this little piece right here, right? Because I've got overlap. And so the total distance ends up being all the way across the major axis. That ends up being 2 times A. Let's go back here and look at that again. Again, when I am at this location and I'm taking the green segment and the red segment, adding them together, it's going to be a distance of 2A. So what that tells me is that no matter where I am, if I add these two segments together, the total distance will be 2A. So what if I go right here to where this point on the ellipse is directly on what we would consider the y-axis, so that the length of these two is the same, right? Well, let's see. Watch this little thing here. This is going to take one segment and put it onto the axis. This is going to take the other segment and put it onto the axis. I can see that both of those are identical. They fill the whole thing. And since we just said that the length there was 2A, then each of these is going to be A in length. So what does that mean? That means that when I have this drawn and I have these two line segments, this is the length of A, this length is C, and this length here is B. And that's where I'm getting that relationship, that A squared, which is the hypotenuse here, is the same as C squared plus B squared. That's the relationship that we're using in the ellipses. And oftentimes we're only given two of the variables in question, and we have to use that equation to find the missing one. So back over here, let's tackle some examples. Let's find the vertices. And the foci of the ellipse. 9x squared plus 4y squared is equal to 36. Again, this looks similar to the examples that we had for circles, but notice that the coefficients in front of the x and the y are different, and that's how we know that it's not a circle. To get it into the format like we had above, we'll divide both items by 36. Notice that in both of these examples, on the right-hand side, the number is always going to be 1. So we divide by whatever that number is that's on the right-hand side. So we divide everything by 36. So I'm going to end up with x squared over 4 and y squared over 9 is equal to 1. Now, again, remember that a is always the larger number. And so in this case, a is going to be here. This is a squared. And b is going to be here. This is b squared. So I know that this ellipse is going to be elongated sort of up and down, right, in the direction of y, because the larger number is under the y squared term. So we know that a is equal to 3 and b is equal to 2. Now let's use that Pythagorean identity to find c. c squared is equal to a squared minus b squared. So that'll be 9 minus 4. So I think c is going to be the square root of 5. X squared and y squared are just on their own. They don't have any additional numbers. So that means that the center of this ellipse is going to be at 0, 0. So we have enough information to get a rough sketch of a graph here. Okay, so on the minor axis, which is going to go left to right, we'll go out 3. Oh, no. On the minor axis, we're going to go out 2, right? 2 in each direction. Sorry. So we're going to go here and here. And then on the major axis, we're going to go out 3 here, here. For the foci, square root of 5 is approximately 2.2. So I'll put those points at about maybe here and maybe here. And then my ellipse, bear with my drawing. It's going to be something like that. Not too bad. Again, if you want an exact graph, you can use Desmos. It won't put the foci there for you, but you get the idea of what the graph looks like. Okay, let's look at another example, slightly different, a different way of giving you the problems. Let's suppose that we are given the vertices, negative 5, 0, and 5, 0. And those are the on the major axis. And that the length of the minor axis is 6. So the center is going to be in between these two vertices, right? So let's put a graph together here. Oops. So I've got one vertex here, and I've got one vertex here. So just looking at that, I can see, well, the center of this is going to be at 0, 0, right? And then the minor axis has a length of 6, so that means that B is going to be equal to 3. We know that A is going to be equal to 5. And then we'll figure out what C is. C squared is going to be A squared minus B squared. So that'll be 25 minus 9, which is C is equal to 4, right? So the foci are going to be here and here. Negative 4, 0, and 4, 0. All right, so we know what the graph looks like, but what is the equation, right? What's the equation of this? Well, I know that I'm going to have x squared and y squared like this because the center's at 0, 0. I know I'm going to have equal 1 on the right-hand side. The larger number is going to go under x because it's going right to left. So this will be a squared, which is 25. And then the b squared will go under y squared, so that will be 9. So this is the equation of the ellipse in this particular case. One thing that I don't think that I mentioned is that when you have a plus in the middle, that's how we know that it's an ellipse as opposed to a hyperbola. Hyperbola will have a minus in the middle. And I'll have a video about that and just make a video about later on today. Okay, let's do one more example sort of similar to this, and then we'll do some sort of challenge problems. All right, so let's find the equation of an ellipse with vertices 0, -6, and 0, 6, and the foci at 0, -4, 0, 4. All right. So this one seems like it's going to go in the direction of y. So my two vertices are here and here, and the foci are here and here. So it still looks like the origin is going to be the center, right? We know that the length of A is going to be 6, that's on the major axis, and the length of C is going to be 4, because that's from the center to the focus point. So then we'll use this relationship to find B. So 16 equals 36 minus B squared. B squared is equal to 20. So B is equal to 2√5. All right. So 2√5 is about 4.5. So we're going to go maybe about out this far for these directions. And so our ellipse looks something like this. Squint and pretend it looks good. All right. So now we need our equation. The center's at 0, 0, so we'll know we'll have x squared and y squared in the numerators, 1 on the right-hand side. A, we said, was 6, and that's going to be in the direction of y, so 36 will go here. And then B was 2√5, so that means we're going to put 20 here. So this is, I forgot my equal sign. This is the equation of our ellipse. Okay.